postulate a classical form for the canonical partition function. It was based on Boltzmann statistics, which of course is the natural place to start. It looked absolutely straightforward, but buried in it was an assumption, so this is a postulate, because this came out of, quantum mechanically, out of the assumption of non-interacting particles, and here we're allowing interactions between particles. This is our starting point, and we see that in the case of conservative systems, that is, where the potential energy depends only on position and not on momentum, the classical canonical partition function factorizes in this way, and the momentum part is straightforward. What is new is the potential part. Thus far, we've only dealt with the absence of potential energy, but we can see this as the configuration integral, and we'll have to deal with it later. Okay.
Where'd you get b to the n for the configuration integral?
So if u is equal to 0, then eta minus beta u is equal to 1. And so this just becomes the integral of dq1, 0 to a, where a is the box size, times the integral of dq2 from 0 to a. Well, let's assume a cubic box for now, it doesn't matter. Which is what we looked at before. And so this of course is just a, and this is just a, and you multiply them together, you get the volume. Okay? I think there's one other point I want to make here, and that is notice here what we had was the Hamiltonian is a sum of two parts. You can divide it into a kinetic and a potential part. So in this case, it's a separable Hamiltonian, separable into a kinetic part and a potential part. And so when the Hamiltonian is separable, the partition function is then written as a product of, you can think of it as a product of factors. One for momentum, one for position. Right. Well, you can separate Hamiltonians in other ways. We've seen earlier that Hamiltonians for our quantum mechanical systems could be separated into a sum of terms, one for translation, one for rotation, one for vibration, and so on. And then we wrote the molecular partition function as a factor, as a product of partition functions for individual parts. Right? So in general, one can often write the Hamiltonian, and it also as a sum of terms, but we can do so in other ways that are helpful. Remember that in earlier chapters we saw, hey, for translation we can just change our sums to integrals. We can assume that energies are so closely spaced for translation they form a continuum. And we said, hey, for rotation, same idea is good unless you're really, really cold, or you've got a really light element like hydrogen. So you can often, we use the integral approximation for the rotation sum. But for vibration, we didn't do that. We kept the sum. So really what we have already done so far is treat some degrees of freedom classically and other degrees of freedom quantum mechanically. You can generalize this idea, and you can consider a Hamiltonian that is a mixture of classical and quantum mechanical Hamiltonian. You can write it this way. And if you do that, then the molecular partition function can be written as a product, and the system, the canonical partition function can also be written as a product. So we'll find that convenient to do sometimes. Separate our degrees of freedom into those that are treated classically and those that are treated quantum mechanically. If there's no problem, we can use this approach. Okay? That kind of covers all of this. And since I have to leave early, I think we'll stop with this. I think we can cover the rest of this in one period. Okay? So the homework's due, just to me sometime today. I will put up a third problem set that will be due in a week, so it'll be shorter. But that way you'll have 3 problem sets before the test. I think that's a good thing. Okay?
Chatfield.
Mm-hmm.
I'm applying for DOI. Can you write a letter?
Sure. You should write me an email so it's there.
Yeah, that's fine.
Yeah. When we do a video interview, why should you get DYF funding?